Hello, hello, hello. All right, we're going to learn today about something that's pretty powerful, actually. We're going to begin the process of learning about what are called triangle ratios, right triangle ratios in particular. And in this video, we're going to focus on the right triangle ratio that's known as the tangent ratio. And the goal is that you will use the tangent ratios to find the length of an unknown leg of a right triangle. All right, now I want to discuss this idea of triangle ratios with you. And I want to do that actually using some triangle ratios that we've already learned without necessarily calling it that. Those in a 30, 60, 90 triangle. And in these two triangles, what I'm asking us to figure out here is what is the ratio of leg 1 to leg 2? Well, if we look in the first triangle, you can see the exact relationship that you're used to seeing with 30, 60, 90. So you can see that the longer leg is the square root of 3 times the length of the shorter leg. And happens to be the same case here. The longer leg is the square root of 3 times the length of the shorter leg. Now here's the ratio of leg 1 to leg 2 in the first triangle. You've got 4 over 4 square root of 3. And if you go ahead and simplify that ratio by doing the canceling that you can do, you get 1 over the square root of 3. And if you like to go ahead and rationalize your denominator, you get the square root of 3 over 3. I'll trust that you can do that work. But if you will just notice this part right here, actually it'll be sufficient for what we're trying to do in this video. Now if we look at the second triangle and we do the same thing, make a ratio of leg 1 to leg 2. That's going to equal 10 over 10 square root of 3. And you see how the 10s would cancel there as well and leave you with 1 over the square root of 3 again, or equal to the square root of 3 over 3. Here's the point that I want to make. Anytime you know the acute angle measures of a right triangle, then the ratios between the sides of those triangles are always going to be the same, no matter what size the actual triangles are. Clearly this triangle is much bigger than this triangle, but the ratios between the legs in this triangle are the same as the ratios between the legs in this triangle because those triangles have the same angle measures, or in other words, because those triangles are similar to one another. Alright, now the fact that similar right triangles always have the same ratios between the lengths of their legs is very useful to us. And I do want to prove to you that it happens in every right triangle with this size. Let me make one more 30, 60, 90 triangle. Alright, and let's just say we call this the short leg x, so it could be any measurement, right? Well, what we know about the 30, 60, 90 triangles then would tell us that the longer leg would be x squared of 3. And then if I make a ratio between leg 1 and leg 2, it's equal to x over x squared of 3. Now remember, x could have been absolutely any number. And the exact same thing is going to happen here. The numerator and denominator have a common factor they can cancel out. And you end up with 1 over the square root of 3 as the ratio between the long leg, or the short leg and the long leg. Alright, every similar right triangle will have the same ratio between its legs as any other triangle that it is similar to. And that ratio is something called the tangent ratio. Now I'm going to write down a definition here. I just mentioned the word tangent ratio. A tangent ratio is the ratio between the opposite leg and the adjacent leg from an acute angle in a right triangle. All right, the ratio between the opposite leg and the adjacent leg from an acute angle in a right triangle. Now, I've got a couple more right triangles for us to look at, and several things that I need to do. I need to explain to you what the terms opposite leg and adjacent leg mean, all right? Now, always, whenever we're trying to make a ratios between the legs of a right triangle, we're going to do so in reference to one of its two acute angle measures. In this case, I'm going to do it in reference to angle X in the top triangle and angle Y in the bottom triangle, okay? And the opposite leg from an acute angle is always the side of the triangle, or the leg of the triangle does not touch that angle. Now, that would mean that this would be the opposite leg from angle X. You can see this side of the triangle does not touch that angle, so they're opposite from one another. And in the bottom triangle, the opposite leg from angle Y would, well, be in the corresponding position, right? So those are the opposite legs. And then the adjacent leg. Now the word adjacent means next to. And so whenever we're trying to figure out which side of the triangle is the adjacent leg to an acute angle, we're looking for the side of the triangle that's right next to it. But more specifically, we're looking for the leg, not the hypotenuse, but the leg of the right triangle that's just next to it. Now you can see that there are two sides of the triangle that touch this angle, and an adjacent leg always touches the angle. But this is the hypotenuse, this is a leg, so that means here is an adjacent leg. All right, and then similarly, when we're looking at angle Y, it has two sides of the triangle adjacent to it, this one and this one, but it's the leg that we care about. There's the adjacent leg to that triangle, or to that angle in the triangle. Now, when we make a ratio between the opposite leg and the adjacent leg, that's called a tangent ratio. And I'm going to write two equations here. One for the small triangle, one for the big triangle. In the small triangle, here's how we could write an equation that relates its tangent ratio. We could say that the tangent of x degrees. Now, whenever we're talking about tangent, we're always going to write tangent as TAN. We're going to use the first three letters as an abbreviation. And then we're always going to put either the name of an angle or an angle measure immediately following it. All right, you'll learn a lot more about that as we go. But the tangent of the x degrees, this angle right there, equals a ratio between its opposite leg, which is A, and its adjacent leg, which is B. Okay? And in this triangle, we could say that the tangent of y degrees is equal to its opposite leg over the adjacent leg, which is C over D. All right? Now, the big fact that I need you to take away from this, now that you hopefully understand some of the details, is that in two right triangles, if they have equal angles, in other words, in this case, if angle X is congruent to angle Y, then the tangent of x degrees is equal to the tangent of y degrees. Now that might not seem like much. I'll try to elaborate that on a moment. That also would mean in this case that the ratio between A and B would have to equal to the ratio between C and D. All right, so suppose that this angle is 40 degrees, and so is this angle right there. What I'm saying to you is that any right triangle that has a 40-degree angle, the ratio between its opposite leg and its adjacent leg is always going to be the same. No matter what size the actual triangle is, the ratios are equal to one another. And that is very useful, as I've already stated here. Now let's use that fact. I have two different triangles here in which we're going to find the value of x. You notice in each triangle, I've given you the length of one leg, and I've given you the length of one acute angle measure, and I'm asking you to find the length of the other leg. And we're going to use a tangent ratio to accomplish that. Now, hopefully you've taken the time to copy the pictures already. If not, pause and do so. I'm going to continue though. Since we have a triangle with a 51-degree angle, every triangle with a 51-degree angle has exactly the same ratio between its two legs, all right? And so what we're going to be able to do is use that predefined ratio. Somebody has figured out what the ratio between the opposite leg and the adjacent leg of a 51-degree angle is, and they've called it the tangent of 51 degrees. Okay? Now, I'll tell you how to use your calculator to work with that here in a moment. But what we're going to do to find x is we're going to take the tangent of that 51-degree angle, and that tangent has to be equal to the ratio between the opposite leg and the adjacent leg. So the opposite leg has to go on top here. That would be x over the adjacent leg, which is 20. And then in order to find out what x is equal to, well, we're going to always get rid of the denominator in the equation by multiplying both sides by that denominator. If we multiply both sides by 20 here, we're going to get 20 times the tangent of 51 degrees is equal to x. That denominator would have canceled out, right? All right, now here's where your calculator is going to come into play. These, these ratios are predefined values that are programmed into your calculator. One thing that you need to make sure you do is put your calculator into degree mode. Now, if you're not sure how to do that, ask your teacher, ask a classmate, but they can tell you how to put your calculator in degree mode. If you don't do that, what we're doing will not work. But once you have your calculator in degree mode, you could type in the tangent of 51 degrees to see what it's equal to. It's equal to a number. But what I'm interested in doing is knowing what 20 times the tangent of 51 degrees is. Well, I guess I'll do that in 2 steps here. The tangent of 51 is about 1.235. All right, and if you multiply that by 20, you'll get about 24.7 as the length of the missing side. Now, I would much rather you just type in 20 tangent of 51. Whoops. I'd rather you type in this entire value at once on your calculator because your calculator can handle that. You don't need to change the tangent to a decimal. But I just wanted to show you that it is equal to a number first of all. All right, excellent. Now I'm going to come back and show you an alternate way to get that same solution here in a moment. But let's go ahead to part B and see what we can do with that. All right, now again we have an acute angle measure where we know the length of one leg. We're trying to find the length of the other leg, and we can use a tangent ratio to compare those two. And it's going to be the tangent of 40 degrees. And it's always equal to the opposite leg over the adjacent leg. From the 40-degree angle, the 12 is the leg that doesn't touch that angle, so it's the opposite leg. That's going to go on top here in my equation. And then the adjacent leg that does touch the angle goes in the bottom. All right, now just like before, to get x by itself, I'm going to start off by multiplying both sides by the denominator. It just happens this time that the denominator is the variable, and that's going to add one more step to my thing compared to last time. To my work, I mean. All right, so we're going to get x times the tangent of 40 degrees is equal to 12. All right, now, essentially my variable is joined to that tangent ratio by multiplication, and so we're going to use division to separate them. We're going to divide both sides by the tangent of 40 degrees, and you can just type that into your calculator the way that you see it right there, and we're going to get approximately 14.3 to 1 decimal place, which is how I told you to leave your answer. All right, so hopefully that makes a little sense. Now, I said I was going to present an alternate solution to part A. I'm going to do that for both of these actually, and I'm just trying to make a small point here. Whenever you're trying to make a ratio between the two legs of a triangle, right triangle, to find one of them, well, it doesn't matter which of the two acute angle measures you use. I used the ones, of course, that I gave to you, but let's say in this triangle A, we had wanted to use the other acute angle measure. All right, now that other acute angle measure would have to be the complement of this one, so it would be 39 degrees. All right, and if I try to make a tangent ratio in relation to that 39-degree angle, what happens is the opposite leg and adjacent leg switch with one another. From this angle, 20 is the opposite leg, not x. So you would have said tangent of 39 degrees equals 20 over x. Then you would have multiplied both sides by the denominator. Then you would have divided both sides by tangent of 39 and use your calculator to determine what that is. And what you're going to find out is that we got exactly the same thing as we did whenever we used the 51-degree angle and took the tangent. We got 24.7 both ways. All right, same idea here. Instead of using the 40-degree angle, I could have used the 50-degree angle. And what would have happened there then is, again, the opposite leg and the adjacent leg would have switched with one another. From the 50-degree angle, the tangent is equal to x over 12, not 12 over x. And say you get 12 times the tangent of 50 degrees equals x. Well, that happens to be the same thing as 12 divided by the tangent of 40 degrees. They both give you 14.3. All right, there you go. So that's how you use a tangent ratio to find a missing side length, and you have choices as to how you do it. While we're working with trigonometry, which is what we call this that we're doing, we're going to always work with word problems whenever we get the opportunity, and I want to do that here. Here's a word problem we're going to solve using a tangent ratio. It says that a scout in a lookout tower 30 meters high notices an arriving army. He calculates the angle of depression of the army from the tower to be 3.5 degrees. How far is the army from the tower? Now you can imagine knowing how far away an approaching army is very important because it gives your defenses time to, bolster themselves, I suppose you could say. Now what I'm going to do is I'm going to draw a right triangle that's going to model this situation. And here's what's going to be included there. In this picture, we've got a tower that's going to be represented by a vertical line, and the army and the tower are both going to be along the ground somewhere. So let's say that this is the ground, and that this vertical line right here is the tower. And now I'm going to connect the two right there and finish making a right triangle. Now vertical lines are always perpendicular to horizontal lines, and you've got this army that's over here. We'll just let this point represent where that army is located. And here is the top of the tower, the lookout guy right there. And so I'll just call that point T for the top of the tower. Why not? Okay, now what it tells us is that we know the tower is 30 meters high. So I'm going to label that over here. And it also tells us the angle of depression of the army from the tower. Now basically what that means is it tells us what angle did the lookout person have to rotate his head down in order to be able to see the army. And one thing that you're going to have to do, you're going to have to get used to working with angles of depression. You're going to have to get used to them always being in comparison to a horizontal line. If the lookout tower guy was just looking straight ahead, he wasn't rotating his head up or down at all, this is kind of the way he'd be looking, right? And what the angle of depression is supposed to show you is how far down does he have to rotate from his normal eye level in order to see the approaching army. And so that would represent this angle right here. That would be 3.5 degrees. Now that information is going to be enough for us to find out how far the army is from the tower, which would be this horizontal distance right there. We'll say that's X meters away. Now you always, in order to use a tangent ratio, have to be making a comparison between the two legs of a right triangle, and you always have to know one of the acute angle measures of the right triangle. Now, think about this. Don't horizontal lines always have to be parallel to one another? And the reason why I say that is because this horizontal line that I made up here has to be parallel to the ground, and whenever you have parallel lines cut by a transversal, as the hypotenuse of that right triangle does, then you've got congruent alternate interior angles, okay? So we know that this angle is also 3.5 degrees. And now that can be our reference angle, right? From the 3.5 degree angle, we know the length of the opposite leg and we're trying to find the length of the adjacent leg. So we can use this equation. The tangent of 3.5 degrees is equal to the opposite leg 30 over the adjacent leg x. Now let's do a little bit of algebra. We'll multiply both sides by the denominator, get x times the tangent of 3.5 degrees equals 30. Then we'll divide both sides by the tangent of 3.5. And whatever that comes out to will be the distance the army was from the tower at the time that the guard sighted them. And that's about 490.5 meters, if we round to one decimal place again, as we did with the previous example. All right, hopefully that's enough time for this scout to alert the rest of his army that they've got somebody approaching. Alright, you see how to use a tangent ratio. In the next video we'll learn how to use sine and cosine ratios to accomplish a very similar thing. Thank you for watching, everybody. Good luck. See ya.